So today we will continue with our discussion on something rather non-trivial. It has to do with the helium excited state, but the implication is much more than that. We will see at the end that it is closely related to the origin of ferromagnetism. The question is posed as follows, using the simplest many electron atom, namely helium. So we were thinking about a low-lying excited state, not very high excited state, that is. So we are thinking about one electron in the independent particle approximation 1s and then a 2s. And then last time we introduced a important principle, namely many electron wave functions must be antisymmetric with respect to interchanging two particles. And with 1s and 2s, they are different spatial atomic orbitals. Therefore, we have two possibilities. The spatial part can be constructed as a symmetric a symmetric wave function. So we have a symmetric spatial part that can go with a spin antisymmetric part, namely the S equals 0 combination. That is the singlet state. Similarly, we can construct an antisymmetric space part to go with the S equals 1 triplet spin state. So altogether, there are 4 states. That is natural. Even with cartoon form, we know that there are such 4 possibilities. But the legal way to write down the wave function to satisfy the general principle that 2 electron wave function must be antisymmetric, we have these 4 possibilities. All of them obey the antisymmetric requirement because we have one part being symmetric, another part being antisymmetric. An interesting story, an interesting question then follows. Will these 2 states, excited states, have the same or different energies? Last time, we argued qualitatively that they should have different energies. For the reason that we introduce some common sense, it is a high-level quantum mechanical common sense that when the spatial wave function is symmetric, the TA also did this week, the wave function or the probability density, the wave function square, will show that the 2 particles tend to be closer to each other. That is to say, when x1 is close to x2, the 2 coordinates of the 2 particles, the wave function square is bigger. That is the Bohr interpretation. In contrary, if we construct a antisymmetric spatial part and plot the same thing, most noticeably, if you go along the diagonal line, this is the x1 equals x2 line. That is 0. That is to say, by antisymmetric spatial part wave function, you have no probability of finding the 2 electrons to be at the same location. Even if you look slightly farther away from this line, the wave function square is not big. So that is a very profound physical sense you must acquire. With an antisymmetric spatial part, the particles tend not to like each other. In other words, they try to avoid each other. But you must understand that in plotting this, we are using, in this example, the harmonic oscillator single particle states. We assumed no actual physical interaction between the particles. There's no Coulomb stuff. There's even no gravitational attraction or anything else. Only by the symmetry property of the spatial part, there is some effective attraction or repulsion between identical or indistinguishable particles. This is a very important fact. In your thermal and statistical physics course, you will do ideal Fermi gas or ideal Bose gas. So-called ideal gas means that the fermions don't interact. So there's no actual physical interaction. The only thing fermions impose on themselves is that they don't like each other. They must obey the Pauli exclusion principle. Nonetheless, even such a simple thing, non-interacting fermions, non-interacting bosons, they behave very differently. And that difference comes from what we are discussing, namely the symmetric and antisymmetric property of many boson and many fermion wave functions. So we are ready to answer the questions. So last time we were here, we argued that because in our helium atom Hamiltonian, there is indeed Coulomb repulsion. There is an electron-electron repulsion term. Therefore, we expect when the spatial part is antisymmetric, namely it is a triplet excited state, the electrons tend to avoid each other by the spatial part construction. Therefore, the Coulomb repulsive term in the energy, which is positive, will be less positive. In the other case, if you have the spatial part being symmetric, that is to say, the singlet excited state, they tend to like each other, but the Coulomb repulsion term will be more positive. Therefore, we expect energy-wise, the lower energy excited state will be a spin triplet state, the S=1 state, and then the singlet state will be at a slightly higher energy. So that is by qualitative argument, realizing the common sense in the behavior of the spatial part of two particle wave functions. So what we conclude so far qualitatively is the following. The ground state no doubt is a singlet because there's no choice. The spatial part is symmetric. And for the first excited state, it is the triplet one. It has a slightly lower energy than the singlet excited state, with 1 electron in 1s and 1 electron in 2s. Next, we would like to find out what is governing this difference. What is the most important physical effect, but in a mathematical form, that leads to this difference? Here I used some term symbol. We introduced that already in the previous part, but that term symbols is applicable to all atoms. The next page is just to explain why we have this S10, S 3-1 there. But we already introduced the idea. So let's go to the heart of our discussion, the first important physical point today. So we argue that this should be the case, and then we will see in the following pages, actually, it is a very important piece of physics. At the end, what this says is that S equals 1 in this case has a lower energy than S equals 0. Remember, S equals 1 when we add 2 spin half, the 2 individual spins tend to align with each other. They enhance each other to make the S longer. That is the triplet state. For the singlet state, they tend to cancel each other. It's S equals 0. So therefore, in this helium excited state exercise, we discovered one thing. We have this Coulomb term, which is electromagnetic in origin, but that is sufficient to distinguish that this has a lower energy than that, okay? And that is closely related to why we have ferromagnetic materials on Earth, and that we are using it every day. For example, in generator, motor, a lot of things, or a hard disk. So let's see how it goes. So in this section, we will go quantitative instead of qualitative. We already know the answer. It is like this for helium excited state. So let's do some calculation. But at the end, we are not going to do it, work it out analytically. I'm just showing you what is that particular long integral that will make the 2 excited state, triplet and singlet, carrying different energies. What is the key physics? That is the goal here. We are not going to plug in some hydrogenic wave function here and do the integral, so don't worry. But it is actually rather fascinating, so pay attention. So what we are going to do is very simple in physics concept. We want to look for what is this? This triplet excited state energy and the singlet excited state energy. That's easy, right? We know the wave function, the spatial part times spin part. All we need to do is to get the expectation value of the helium Hamiltonian. That is the expectation value of energy. All right? Now, as explained last time, the helium Hamiltonian is spin independent. It does not carry spin here. Formally, the 2 electron wave function has a spin part here and has a spin part there. But because of this does not have any spin part, the spin part in the product will give us 1 because we already normalize it. We have this 1 over square root 2. Therefore, it looks as if the spin parts disappeared, but they disappear for some good mathematical and physical reason. So even if I turn the page like this, I cannot write it in 1 line. So I hope that you already digest that the spin part already disappear from the calculation. But they don't just disappear. They give 1, okay? And now, that is the singlet. Singlet spin part is antisymmetric. So the spatial part is 1s, 2s, and then plus, and then switch the spatial coordinate. And this is this plus sign, make it symmetric spatial part. And then we have to insert the helium Hamiltonian in the middle. So let's count how many terms. Don't be scared. I'm not going to write it out for you. We have two terms here, okay? But each term has some product of wave function, but two terms, 5 terms. There are 2 terms here, kinetic energy, and an electron 1 sees the nucleus. We have another 2 terms here, and then we have this Coulomb repulsion. We know this Coulomb repulsion is the term that it's giving us trouble, right? That makes any multi-electron atom problem hard to solve. 5 terms here, so we have 5 terms. Then we have another 2 terms. So how many integrals we have to do now? Do you know what's going on? I have to pick this, multiply into this, and then multiply into this and do this integral. That's 1 term. You understand? Okay, so I have many terms here. Don't worry about it. Now, let's think about the triplet state. The triplet state have almost the same form, only that the spatial part must be antisymmetric to go with the spin triplet. So instead of a plus sign, I have a minus sign. All right. Now, even without doing anything, you realize that they cannot be the same. Agree, right? I have a plus here, I have a minus here. So from the appearance, they are already different. Okay? But you must appreciate one point. This is a very non-trivial piece of physics. The helium Hamiltonian is spin independent, does not depend on spin. However, spin plays an important role in distinguishing the energy between the singlet and triplet state through the requirement that the total wave function must be antisymmetric. It is the spin part symmetry that forces this plus sign and forces this minus sign. Okay, so it is a very fascinating piece of physics. But first thing to note, they should not be the same. All right. Now, a student told me he found 12 terms. Okay, so do that. But I just want to do it schematically. Maybe I will ask you to write them out in a homework problem. Okay, but I think it is sufficient to make the point, and it is sufficiently clear. You can see through the physics, and that is what our course is about. Don't do anything that exact, right? We want approximation. Get the physics that is in agreement with observation. Okay, that is our goal. So now I'm claiming it is this terms that is giving us trouble, right? So I will focus on this term, and then I start writing down some of this with this in the middle, and then go with this. Okay, now think about this. This is 1SR1. This is also 1SR1. If I insert this Coulomb term in the middle, that is exactly our classical interpreted term that allowed classical EM interpretation. That is the term we used to call J. So we will encounter J1S, 2S. Okay, now that is ordinary term. The fancy thing is the following. Please pay attention. Do you see there will be a term? On the left, it is 1SR1, 2SR2. Then the Coulomb in the middle. And then it will pick up this term to do integration. Now, that is very strange. This is 1SR2, 2SR1. Look back on this side. It is 1SR1, 2SR2. It looks as if the wave function on the right-hand side and the left-hand side has the spatial coordinate exchanged. All right. And then with the Coulomb term in the middle, that is the term we introduced and called the indirect Coulomb integral or exchange integral. A term that we call K1s, 2s. Okay, so you see, this kind of term appears. Similarly, this kind of term also appears in the triplet energy. But whenever you have this goes with that, there is a minus sign. But when you have this goes with that, you have a plus sign. Okay, so without doing anything, I'm claiming this important difference. The singlet energy will have some terms, well, many, not some, many terms, but it turns out that the terms here will be the same as the term there. So they are not the key elements that will separate the energy. The key things that will separate the energy are this kind of exchanged energy terms. Okay? You will see something like plus these terms and minus these terms. And that is what make the two triplet and singlet energy different. So I pause here. Do you get the main physical point? It is the K, the exchange integral, that is causing the triplet and the singlet excited state to have different energy. Can I get my point across to you? So that is just like the energy difference between, yeah, right. Okay. Now, this thing, as we already mentioned, there is no classical interpretation. So it is 100% quantum mechanical effect. Okay. This was the integral that we introduced in the previous part. K, called the integral K, and the subscript 1s, 2s means we have two states, and once labeled that way, actually you can write down this integral. Okay, so the point is that it is due to a non-classical quantum effect. Here, I have not made everything exact. I'm saying that terms like, of course, there will be more terms like this, right? Because you can start from, where's my pointer? Here, you pick up the Coulomb and you go with the first term. That will be another exchange integral term, right? Or you start with this minus sign, Coulomb, and then go with this term, again, another K integral term. So that's why I claim there are terms like this. But I think this sign, I get it right because of the different symmetry. Okay? So this was the integral that we introduced previously, generally two state, spatial state AB. Spatial wave function, AB, this is the exchange Coulomb integral or simply exchange integral. Many will even call it exchange energy because it is an energy. It is an expectation value of the Coulomb repulsive energy. Okay, now it should be contrast with the direct Coulomb term we already discussed that has classical interpretation. Now, this thing is very difficult to explain. All you need to do is take this page, spend 2 minutes, look at it, up, down, then you realize, this A, B, R1, R2, they are put in a funny way, all right? So now, we have to appreciate what we did. The first thing it did is qualitative. We just say, let's look at some common sense of a spatial wave function. But then we have to do something more quantitative, as we just did. I haven't done the whole thing for you, but at least the main physics is already brought out. So doing this, we have one appreciation of nature. Spin plays a role, but it is this Coulomb interaction. It is the electron-electron repulsion that leads to the difference in the energy. You see, put this thing in the middle, that will give us this exchange term. So the origin of preferring spin alignment over S equals 0 comes from the Coulomb term. Okay, it's rather a highly non-trivial point. Then we get a big byproduct. This is part of solid state physics, but I would like to bring out the physics here. Then we will have ferromagnetic materials, or make it even bigger, we will have anti-ferromagnetic material. A ferromagnetic is 铁磁. So there are magnetic materials, but there are not many of them. So you look around in the periodic table, only a few atoms, when they form a solid, they will be ferromagnetic materials. Those are mostly in the 3D so-called transition metal role. For example, iron, cobalt, nickel, then they have a few so-called 3D electrons occupying the D levels, but according to quantum mechanics, we will discuss it a bit in the next part. This, for example, if you have 5 electrons to be put in the 3D state including spin will have 10 states. Then what is the lowest energy way to put that? After you do many quantum mechanics calculation, you try all the ways. Then you can sort out which one is the lowest energy, right? It turns out to be up, 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 up. So when you have this, there will be a very good spin angular momentum alignment, giving the atom a rather big net magnetic dipole moment. And that is the origin of magnetism. And in our discussion, we know that spin plays a role. Okay, so ferromagnetic material has the following property. It is not, because if you read E and M very so well, in Griffin's book, then you may look up, I have 2 magnetic dipole moment, mu1, mu2. What is the interaction energy between them? Then I copy from the book this expression. All right. Now, the point is that after you know the net spin or net magnetic dipole moment of an atom, you can put the numbers in here. It turns out that the number, this interaction energy, is too small to justify that we will have room temperature, we will have at room temperature ferromagnetic materials. Now let me explain. This is a little bit of thermophysics. In thermophysics, thermal means thermal energy, it's kT. But thermophysics, the temperature tends to randomize things, right? For the reason, at finite temperature, I think many of you will have your midterm next week, right? The thermal and statistical physics. So I hope that by now you know, at finite temperature, you are trying to minimize the Helmholtz free energy. Okay, do you know that? 學咗未? Okay, good. Now, good. Now, so you know, temperature would like to randomize things, and when you randomize things, entropy is higher, and this minus sign will help minimize the Helmholtz free energy F. So that is the whole story, right? So temperature want to randomize things. Why? Because that helps. Because it's minus Ts. So it will lower the Helmholtz free energy. So if we believe that this ferromagnetism, when atoms have magnetic dipole moment, and it is because their classical EM interaction, that is the cause to make them align together. A ferromagnetic material means even if you don't apply a B field externally, there will be a magnetization. This is called spontaneous magnetization. In Chinese, it's a 自发起性啊，自发的起性。The origin of it is that the tiny magnetic dipole moment in the solid, they will align by themselves along some direction. Okay, so this will tell the neighbor, align with me. And then this will tell the neighbor, align with me. So this local information, hey, align with me, will make a global collective alignment. That is the physics behind ferromagnetic material. So the story I was trying to tell you is the following. You take some classical expression, interaction between two magnetic dipole moment, perhaps due to spin, for example. You plug some numbers into it. For example, the spacing between them may be one atom separation, and then you plug some number into it, you will find this energy is too small. What does it by too small? If I use kT of room temperature, that is already much bigger than this particular energy. Therefore, in the competition, thermophysics, kT compete with some energy in your system, kT wins. When kT wins, kT tend to randomize. That is to say, when this magnetic moment tell the neighbor, align with me, but there's some temperature, thermal thing, want to flip, make it disorder, okay? It's the thermal energy that wins. Therefore, we don't expect to have ferromagnetic material at room temperature. But the fact, experimental fact is that we have magnets to play with. We have magnets to install in our PC, in our the motor, in cars, roll down the window, things like that, okay? So that is not the origin of ferromagnetism. So what is the origin? We have seen the origin already. In helium, you know, the lower energy state is spin triplet. In spin triplet, the two spin tend to align, and the origin of which is Coulomb. Coulomb energy is much bigger than this dipole-dipole interaction energy. Okay, so that is the reason behind it. After understanding this reason, it is Coulomb behind the scene, but exchange integral due to quantum mechanics. These are the origin of having this interaction between neighboring spin and tell each other to align. After that, then physicists wrote down many so-called models for ferromagnetism. So here, I just want to give you a picture of this kind of model. We considered the two spins in the electrons in the helium atom. So we have, if I divide it by h bar, then this thing has no unit, and therefore that must be the exchange energy term that is setting the scale of the energy gained if they align. Okay, now we also learned some spin orbit interaction, a hyperfine structure. They are all of this form. When you have this form, you know, add them up. S equal 1, S equals 0 is the best way to treat it. If you do this, if you do that, then you will see that the S equals 1, the spin triplet will be lower, the spin singlet will be higher, and they are off by this amount. Okay. And now, in a piece of ferromagnetic material, we don't have only 2 electrons. We have an array of spins, or an array of atoms. Each has some spin, net spin on it. Therefore, ferromagnetic models will have to sum up this kind of terms in an array. So in a cartoon way, I say sum over ij pairs. The simplest thing is to sum up nearest neighbor pairs. Now, this is very profound idea as well. By summing up nearest neighbor pairs, this interaction is short range. That's reasonable. Well, we're doing quantum mechanics. It's not so far away things in interaction anyway. But the key thing is that, let me introduce the name first. This model is very popular in investigating magnetism. It is called Heisenberg model of ferromagnetism. Now, that is nothing surprising. You know, it is very quantum mechanical in its origin. I mean, this K comes from the exchange integral, or even people will call it Heisenberg exchange energy, but this K. It was proposed in 1928. I was talking about even when we only sum up nearest neighbor interaction, we will have alignment of all the spins in our array. That is long range order. So let me give you the punchline one more time. Short range interaction could lead to long range order. Now, that is something I think is one of the biggest discoveries in humankind in the 20th century. You don't need long range interaction in order to influence another spin far away. All you need is local. Talk to your neighbor. Do this, do this. The neighbor and the neighbor do this, okay? As long as there's a condition, the temperature is not too high. And that temperature is called the Curie temperature. it was found physically for the real ferromagnetic materials, the Curie temperature is something like, let me see, I think 300 Celsius or something. That is to say, much higher than room temperature. And that was the point I tried to make. That classical E&M expression, okay? That classical E&M expression does not predict we would have ferromagnetic materials at that high temperature because the energy scale doesn't fit to that range. So here's a little bit more statistical physics. I like the subject very much. I'm teaching another course this term on statistical mechanics for the MSc students. So it was fun. Okay, so now think like a physicist. So I have this Heisenberg model. Okay, so at 0K, there's no entropy term, right? Minus Ts, T is 0. And we know third law, S should be 0, right? So that term does not carry anything. Therefore, the whole thing is to minimize energy. The minimum energy will be ordered, right? Because when you do all the alignment, each pair, you will gain some K, minus K, because there's a minus sign, lower when they align. And now, when T is not 0, it is not the energy U that you want to minimize. Instead, it is this thing you need to minimize, okay? That is the equilibrium statement, right? A system, TVN, okay, at equilibrium, F is minimized. So, and this is the entropy term, and therefore, temperature will tend to flip some spins. So at low temperature, still okay. A few of them get flipped, the energy is higher, this will be higher, but this will be lower. And this term will be sufficient to compensate the increase in the U. So there will be some spin flipped. Nonetheless, the majority is still going up. You still have a net magnetization. When you increase the temperature bit by bit higher and higher, this flipping will occur more in more spins. Therefore, the net magnetization tends to drop. At something called the Curie temperature, okay, then on average, there will be as many up as many down, and therefore the magnetization becomes 0, and that is the Curie temperature. And you can almost estimate what is the Curie temperature. It must be related to our energy scale divided by K. So this is roughly the Curie temperature. Roughly means I'm off by a factor in front. This factor has to do with what is my lattice. How many labors do I have, right? In a 1D chain, I have 2 labors. In a 2-dimensional square lattice, I will have 4 neighbors, etc. The interaction between pairs, there will be more pairs when you have more neighbors. Thereby, that Curie temperature is off by a factor. Okay, nonetheless, the physics is very clear. So final words. I would like to just mention what is the fork. I have already mentioned many times, Hartree approximation. But more generally, usually it's called Hartree fork approximation. We introduced the Hartree approximation easily by considering the helium ground state. We know that we have to assume a ground state to write down a Schrödinger-like equation to solve for that unknown ground state in a self-consistent way. That is the Hartree way, as I remind you here. Okay? But now, when we have more electrons, they will occupy higher levels. The 2s, lithium, 3 electrons, so 2 in 1s ground state. The third will be in 2s. How can I write down some equation to solve for 1s and 2s? There will be a set of coupled and self-consistent equations. So what I want to point out is that when you write down the equation to solve for 1s, there will be some strange-like term appears in the Schrödinger-like equation. The Schrödinger-like equation must carry things like 3 factors of wave function, right? You have 2 factors here, you have the third here. So here again, I have 3 factors, but this is different from that. Therefore, I cannot multiply them together and think about it as a charge density spreading out in a classical EM way. There's no such interpretation. And you will have this kind of term in the Schrödinger-like equation in your coupled set of equation. This is called the exchange term and also called the Fock term. After a Russia, Soviet Union physicist, Fock, he did a lot of things in many-body theory. So when you have this term in addition to the Hartree term or in one equation, that is called the Hartree-Fock approximation. Again, you need to do self-consistent solution. Okay, so that is the end of this part. So let us take a short break, and then we will finish the last part of this module on the physics of atoms.